Now, as I told you in a previous lecture that we have a relationship between the Kp and the Kc, and I think you remember what is Kc actually. I'll just write again for you for a general reaction, right? Suppose we have a general reaction, this reversible reaction in which A plus B forms C plus D, and simultaneously the C and D has a tendency to form A and B again, right? So like if we have reached the stage of equilibrium, that means the rate of forward reaction becomes equal to the rate of reverse reaction, then at that time we can write the equilibrium constant expression for it, right? So as I'm doing it, I'm writing an equilibrium constant expression for this equation, and as I told you that when we write the equilibrium constant expression, it is equal to the concentration of products, right, and divided by the concentration product of the concentration of the reactants, right. So we write in this order when we talk about Kc, right. Whenever we wish to write for an expression for Kc, we need to write like that, right. If there are moles also present along with it, so it is just simple, you have to put the moles as stoichiometric coefficient, like this I am putting. So this is an expression for a Kc, that is the equilibrium constant expression, right, for K. And if I say that these reactants and products are present in a gaseous state, then instead of writing the concentration, I can write the concentration in terms of partial pressure, right. So I am just writing, considering them as gaseous component, I am writing the expression for Kp. So when I am writing the expression for Kp, it is not a, you can say, a tough task to do that. It is so simple. Just you have to do that in the similar way in which you wrote that the concentration of product to concentration of reactant, just instead of concentration you need to write the partial pressure of product to partial pressure of reactant, and if there are any moles present, just use them as superscript, that is the stoichiometric coefficients, right. So see, I am writing the partial pressure for C, right, we have mole C, so I am writing the mole here. So just the simple way you have to write, so instead of concentration we are just putting the pressure, that's it, right. So similarly I am writing here so this way we write an expression for the Kp, right, and as we have discussed that Kp and Kc are related to each other, and the relation is Kp is equal to Kc RT delta N. You already know now, right. So we are just going to understand that what are the conditions, what are the particular conditions which are required or which just relate Kp and Kc, or we can say when is Kp equal to Kc, when is Kp bigger than Kc, or when is Kp is less than Kc. So we need to have the three different conditions, right. So when delta N is equal to 0, that means there is a reaction that do not involve any gaseous component. So that means the gaseous component, the delta N is going to be 0. I think you know that how to calculate the change in number of moles, but still I'll do a, you can say the example for you. Suppose we have a reaction, I'm writing here H2 plus I2, reversible reaction, 2HI, right. If I wish to calculate the number of gaseous moles, I say all of them are present in gaseous state, and I just wish to calculate the change in number of gaseous moles. So how I am going to do that? Say, see here the moles are 2 moles, right. In this case we have 1 mole, and in this case also we have 1 mole, right. So whenever I wish to calculate delta N, what I have to do, I just have to subtract the number of moles of product, the total number of moles of the product from the total number of moles of the reactant. As we can see, the number of moles of the product is 2, right, and minus, and the reactant is 1 plus 1, so I just write 2. So in this case the number of gaseous moles is 0, right. So that means that like in this case we are getting the 0 value, but in some equations we are getting the value in negative sign, or we are getting the value in positive sign. So anything can happen. It is not like that it is you are always going to get the 0 value, right. You can get either of the value, you can get the 0 value, you can get the negative value, you can get the positive value. So we are just discussing the conditions, that under what conditions the Kp can be equal to Kc, right. So as you can see, if delta N is 0, then what is going to happen, when any reaction does not involve gaseous moles, then Kp will be equal to Kc, right. So this is going to happen when number of gaseous moles if the reaction do not involve any gaseous moles. Or we can say when the number of moles of the reactant and the product are equal, as we saw in this reaction, it do involve the gaseous moles, but the number of moles of the product and reactant were equal, right? So when we just subtract, we got 0. So that means delta N can be 0 under two conditions. One is that when the reaction will not involve any gaseous moles, and the second will be going to that when the number of moles of the reactant and product are the same. So anyhow, either of the case we can use, that means we are getting delta N is equal to 0, which corresponds to that Kp is equal to Kc, right? Now we are going to discuss that under what condition the Kp is going to be greater than Kc, right? So suppose if we have any reaction in which delta N is going to be positive, right? Positive means the number of moles of products are greater than number of moles of gaseous moles of reactant. Then when we will minus the reactant moles from the product moles, we are going to get the answer in a positive manner. So that corresponds to the state when Kp is greater than Kc, right? And we do have a condition when number of moles of product is less than number of moles of reactant. So in this case, change in number of moles is going to be negative. So that means Kp is going to be less than Kc, as in this case Kc is going to be greater than Kp. I think you got it, that under what conditions what is the relation between the Kp and Kc and how they are related to each other. Again I am repeating, you know how to write the Kc expression? Yes, you know now. It is just you have to concentrate that you have to write the concentration of product divided by concentration of reactant, that's it. And just keep in mind, don't put the plus sign, because it is the common mistake with the child do when they just saw a question and they just hurry up and just you can say in a rush they just write the plus sign. It is not plus, it is product. See, so just look here and don't make this kind of mistake, right? It is a multiplication, right? And if it involve a gaseous component, we can do write the expression in term of the partial pressure that we have done. Just write the partial pressure of name of the component, that is the reactant or product, and the moles if they are present. So this is how you can write, right? And we do we derive the equation relation between the Kp and Kc, which comes out to be Kp is equal to Kc RT delta N. How we did in a previous lecture, that is by just putting the value of P equal to, we know PV is equal to nRT from ideal gas equation, P is equal to CRT. So just specifying that, you know that how I have derived this relation. So we just derived Kp is equal to Kc RT delta N, where delta N specify change in number of gaseous moles, right? So we have three conditions. If the reaction do not involve any gaseous component or the number of moles of the reactant and product are same, then delta N is going to be 0. And in this case, Kp will be equal to Kc, right? If we have a reaction in which the reaction involved the gaseous component, but the number of moles of product are more than the number of moles of reactant, then in this case Kp is going to be greater than Kc, right? And if we have you can say a situation in which the number of moles of reactant are more as compared to the product, then the delta N is going to be negative. So obviously Kc is going to be greater than Kp, that means Kp is less than Kc. So these are the different conditions under which we can say that when the Kp is equal to Kc, or when the Kp is greater than Kc, or when the Kc is less than Kp, right? So you need to remember these equations, these are very important. And I think you know now how to calculate the change in number of moles, right? You know that now. I'll just make you practice with few questions so that you have a good hold in these questions, because see, equilibrium, just these Kp, Kc expressions just form the tool of the equilibrium. So you need to be well versed in it, right? So I'm just making you practice with few questions so that you should know how to attempt it and how to just write the expressions for them, right? So we'll be discussing, I think Kp and Kc is clear. It's clear, right? Don't be confused, it is just a matter that you have to just look at the equation and just need to write the expression for the product and the reactant, right? And for the gaseous component, we write in a term of partial pressure. So few questions I am going to discuss. The first reaction we have is N2 plus O2. Reversible reaction 2NO, right? The second one we have H2 plus I2, reversible 2HI, third PCl5, PCl3, Cl2, and the fourth one is the Haber's process, the famous Haber process, that is the formation of ammonia, that is 2NH3. Now what you have to do in this reaction, we have to predict whether Kp is equal to Kc or Kp is greater than Kc or Kc is greater than Kp. So we just have to prove them, right? So see how we will be doing it. We know if you get a question like this, so just do like this. We know Kp is equal to Kc RT delta N. This is the relation. So first of all write like this, right? Now you know that we need to check the value for the delta N, and from that we get the idea that Kp is going to be greater than Kc or Kc is going to be greater than Kp, or whether they are equal or not, right? So in this reaction, all reaction involve the gaseous component. All are gases, right? This I just forgot to write when I was writing the question. These all involve the gaseous components, right? All are gases, right? So taking into the consideration the first expression, so I'm just going to calculate the delta N, right? So how we calculate the delta N? You know, product minus reactant, the moles of product minus moles of reactant. So this what I'm doing here. So it is 2 moles minus reactant 1. We get to see nothing, that means 1 and 1 again 2 moles. So that means delta N is going to be 0, and we know that when delta N is 0, that under that condition Kp is equal to Kc. So this is the result. This is what they asked, that you have to just identify what out of them is what you can see in them, these equations, right? So that means in the first one Kp is equal to Kc, and you know that why? Because change in number of gaseous moles is 0, right? So we look for the second equation again. So again in here the delta N is equal to product minus reactant, product again 2, 1 and 1. So again we are going to get 0, that means delta N is 0. The same result, that is Kp is equal to Kc, right? So now I will be looking for the third reaction. We are going to calculate delta N in this case as well. So here product minus reactant. So how many moles of product you get to see? Nothing is written here, that means 1 is here. Nothing is written in front of Cl, obviously 1 is here, right? And obviously we have 1 this side also. So that means product moles are 2 and the reactant moles is 1, which comes out to be 1. That means delta N is plus 1. And we know that when delta N comes out to be in positive, that means Kp is greater than Kc. So this is the result for the third reaction, right? So similarly we are going to look for the last one as well. So again we are going to calculate the delta N, so product minus reactant. How many moles of product? This you can see 2. Don't use these 3 or 4, right? These are just the, you can say they are just involved in the chemical formula. They don't specify the moles, right? So this is 2 and here reactant 3, and obviously nothing is written to 1. To reactant moles 3 plus 1, 4. So product we have 2. So the answer comes out to be delta N is equal to, you can see 2 minus 4 is minus 2. So that means in this case Kp will be less than Kc. So this is how you are going to attempt the question. If you get the question that you get certain equations and you are asked to predict that whether the Kp is greater or Kp is less than the Kc or Kp is equal to the Kc. So this is how you are going to do that, right? I think it's clear. Now we'll be taking up the next topic. We'll be just using the relations and the questions I'll make you practice, so that you should be familiar with the questions, that what kind of questions you're going to get, because you know what happens in these classes in plus 2 and plus 1, the children are often familiar with the topics but they don't know how to attempt the question. So this as you will practice the questions like we are making you practice, and if you will practice those questions like that, you will have an idea that what kind of questions you are going to get, and then you can just perform easily, right? So this is the reason that I am just making you practice the questions, right? So we have another question. In the second question what we have a reaction right? So this is the given reaction, right? And for this reaction, Kp is also given, which comes out to be 1.8 into 10 raised to the minus 3 kilopascal, right? And the temperature is 700 Kelvin. And you need to find the Kc for this reaction, right? So how you will be doing that? So we know that we have the Kp, we have to calculate the Kc, we can have the N also, we can have the R also, because R is the gas constant, and we do have the temperature, right? So what we are going to do, we are just going to use the relation Kp is equal to Kc RT delta N, right? So I am just putting the values in this relation. So Kp is 1.8 into 10 raised to the minus 3, Kc we have to find out, R comes out to be 8.314, temperature is 700, and delta N we are going to calculate. I think you know how to calculate delta N now. So it is moles of product minus moles of reactant. So that means 3 moles and reactant mole is 2. So it comes out to be 1, right? So we are just enclosing this, and I am just writing 1, and you know that whether we write 1 or not, it doesn't make a difference, right? So this is how we are going to do. So when we have to calculate Kc, I am just shuffling these equations so as to get the unknown variable. So it is 1.8 into 10 raised to the minus 3 divided by 8.314 into 700. Right, and when you will solve for it, you will get an answer 3.09 into 10 raised to the minus 7 moles per liter. So this is how, see how I have done, I have just substituted the value, but for substituting the value you need to remember the relation as well. So relation serves an important issue and you need to remember that, right. So this is how you are going to do the, you can say the questions which are based on the Kp, Kc, like as I told you that you can get the question that you have to predict that whether Kp is greater than Kc or like that, you just have to compare them, right. Or you can get a question in which you have to find the Kp and Kc for a reaction in which one of them is given and one of them is unknown, right. So this is how you are going to do. I will be discussing more questions, but before we do that, I will make you explain one more topic, because we have to, these are minute topics which we will be doing, but on basis of each topic we need to have certain questions as well, because you will be familiar with what kind of questions you get, right. So we have 2 kinds of equilibrium. We did yesterday also 2 kinds of equilibrium, the physical one and the chemical one, right. But that was based on the physical process and the chemical process. But now the equilibrium which we are doing is a homogeneous and heterogeneous equilibrium. If all the components which are present in a reaction, they occur in same phase, then it is said to be homogeneous equilibrium, right. Like if I have reactant, if I am stating an example for you, suppose I have A plus B forms AB and I say everything is present in a solid state. So because they are existing in the same phase, right, you get to see that. So that means it is a homogeneous equilibrium, right. And if there is a certain different kind of, if I say if there is C also present along with it, which is a liquid or a gas, something like that. So you can see here that different states are present. So that means it implies that it is in heterogeneous equilibrium, right. So homogeneous equilibrium means when all the components, whether we are stating the reactant as well as product, they are present in a same phase, right. And when we talk about heterogeneous, they are not present in a same phase. As I told you, like if here is this kind of reaction is present, A plus B solid, AB forms solid, then it is a homogeneous equilibrium. If I write like that, I am doing a general equation, right. So this is present in a solid form, suppose this is a aqueous form, again it is a aqueous form and it is a solid form. So as they are present in different forms, so that implies it is a heterogeneous equilibrium, right. So you are just going to see the phases, and by just looking at the phases you can know that it is a homogeneous equilibrium or a heterogeneous equilibrium, right. So I am just making you practice few questions based on it. So we have the first question. We just have to predict that whether it is a homogeneous equilibrium or it is a heterogeneous equilibrium, right. So this is the third question. So we have a reaction 2NH3 gaseous form, N2 plus 3H2 again in gaseous form, right? The second equation we have is Fe3 positive plus 3OH negative forms FeOH whole thrice in solid form, right? And these are also these are present in aqueous state. The third we have is I2 in gaseous state plus 5F2 in gaseous state, and again we have IF5 in gaseous state. The fourth reaction we will be discussing will be copper nitrate in solid form, copper oxide in solid form plus 4NO2 solid form and plus O2 in gaseous form, right? So first of all, in this reaction the balancing is not required. So until you get the question that yes you need to balance the equation, then only you balance this equation, or otherwise if you just get a question, just predict the homogeneous or heterogeneous, so we know we don't need balancing, right? But still if you have a time, so just balance it, because you know that chemistry understands the language of chemical equation with the full information, right? But if you are short of time, then do not balance it, so just write the question that it is a homogeneous equilibrium or a heterogeneous equilibrium, right? So see how we'll be doing it. So see, it is present in gaseous, again gaseous and gaseous. So that means all components are present in one phase. So it implies it is a homogeneous equilibrium, right? And in this case, we get to see it is in aqueous and solid. So that means they do not exist in the same phase. More than one phase is we can see here. So that means it is a heterogeneous equilibrium, right? So similarly, the third one, the gaseous, again gaseous. That means which implies that it exists in same phase. So obviously it is going to be homogeneous equilibrium, right? The fourth one, this is the solid one, solid, but gas is there. Three components are solid, but one component is gas. So whether the one component is you can say is not similar to the other, or we get to see more than one which is not similar to the other, but still we get to see the two phases, that implies again it is a heterogeneous equilibrium. So this is how you are going to predict that which reaction is a homogeneous equilibrium and which is a heterogeneous equilibrium. And I think it's clear to you. Homogeneous equilibrium just means that when the components are present in the same phase, that means homogeneous equilibrium. When we get to see more than one phase, that means it is a heterogeneous equilibrium. So this kind of questions you are going to get in order to predict that the type of equilibrium, that is the homogeneous or the heterogeneous, right? And one more thing, do not get confused between these types, homogeneous and heterogeneous, with that physical equilibrium and the chemical equilibrium, right? The physical and the chemical equilibrium were based on the physical and the chemical process, right? And in this case it is just based on the existence of the phases of the components. So don't just get confused with it, right? Now we'll be starting with the other topic and we'll practice few more questions so that you have a good command in chemical equilibrium. And it's not a you can say a tough chapter, but it involves many basic phenomena which you will get to see in other chapters too, right? So just we'll be starting with the other topic, that we'll be taking new topic now.